Welcome, folks. My name is Mike, and today I have the pleasure of bringing you a talk from Victor Ciura, who's worked as a technical lead, a principal software engineer, and has built and delivered software across many different platforms for many different companies. In this talk that's catered towards students, he's going to be talking about performance, the standard template library, and the iterative design process, and how to write code in C++. So with that said, I'm going to get out of the way and let Victor take it away in this wonderful talk in which Victor spent some time with us, giving us this wonderful lecture. Let me briefly introduce you, and then we'll get started. And then again, for folks who are watching the recording, this is going to be rebroadcast again a little bit later in the day. So make sure to join, although you'll be missing out on meeting Victor and some of the live participation. So thank you for those folks who are here and on time. I just briefly want to introduce Victor, who is currently a senior software engineer at Microsoft, though he's had a long and great career for 20 plus years as a software engineer, working on various tools to make our lives better. So just to name a few of those tools, Clang Power tools being one of them, working on packaging tools such as MSI to help us, deliver software. And Victor's also been a speaker at universities, so we really welcome him here at Northeastern University, as well as a speaker who I've gotten to know at various conferences like C++ on C, ACCU, all these great conferences I've been telling folks to attend. So when I met Victor and had a chance to talk with him a little bit this past summer, he told me about how he loved giving talks, and I knew he's a great speaker, so I had to invite him here at Northeastern University. So again, Victor, thank you for your time. We'll give you a loud virtual applause here, and I'll let you take it away.
Right. Thanks, Mike, for the intro. It's certainly glad to be here. I wish I were there in person with you, but traveling these times is more difficult than it used to be. But I'm imagining you there, and I do encourage you to just unmute yourself and ask questions. So just make sure I check this. Everyone can see my slides, right? All right. So I do encourage you to interrupt. So I've done, usually when I do conference presentations, folks tend to reserve the questions till the end. So they feel they're more polite if they don't interrupt the speaker, and sometimes that could help. But when doing workshops or lectures at unis, I prefer that students actually ask questions, interrupt. It's okay to take a tangent if you care about a particular thing that I'm going to talk about. I can drill down, go into more details, or explain more in depth some of the concepts that you might not feel comfortable with. So feel free to interrupt anytime. Either post in chat. I'll try to take a look at the chat window, but just in case I miss something, feel free to unmute yourself and just ask away. So I want this to be something that's casual, unplugged, interactive, like a dialogue. So it really helps. So I don't have a lot of slides. I have a bunch of them so that I can give a proper context to what I want to convey today. But we're going to look at code. So I do intend to spend a significant portion of today's interaction going through some code. I'm not going to spend time writing it because that's boring to follow someone just typing slowly. And I type slowly. But we're going to look through some code, various bits of code, and we're going to benchmark some code and see some differences there in different approaches that we're going to take. And I do encourage you to ask about the code. So I'm going to explain as much as I can, but I'm assuming a bit of familiarity with some C++ concepts, not very complicated things. I would consider them like beginner to intermediate concepts in C++, but if you're not familiar with them, feel free to ask. And I'm going to try at each step, I'm going to try to generalize. So there is some general good tips or general good techniques that I think are can be abstracted away from C++ and can be applied in other programming languages as well, if you're interested. So we're going to try to use C++ as the basis for our discussion, but we're going to always try to identify higher level things that are useful in our toolbox as programmers, regardless of preferred programming language. So we're going to start with something that's probably familiar, but worth recapping. So STL algorithms, principles, and practice. And I think some of you might be familiar with this quote from Scott Myers, prefer algorithm calls to handwritten loops, or more modern incarnations that you might have seen from Sean Parent in his now famous C++ seasoning talk, no row loops. So that would be the, the modern incarnation of prefer algorithms. And in general, I would say there's a good instinct, especially when coming out, when learning a new programming language, when doing assignments in uni, when learning something new for the first time. There's a good tendency to structure your thinking in a very imperative way. And one of the first control flow structures that programmers get comfortable working with is the repetition, the for loop. So whenever you feel like going down this path and just reaching out for a for loop to quickly let's quickly iterate something, let's quickly count something, let's quickly filter out something, and you go to a for loop just by inertia, just stop and think. So this should forever from now should be a trigger event in your mind. Whenever you're trying to write a for or a while loop, you should really stop and think, what am I trying to accomplish here? What are the high level goals? And whenever possible, try to move the frame of thought from the how of the problem to the what of the problem. And I'm not going to try to say that you should think in a functional way or think in immutable data structures and think about purity of function and go the extreme. I'm just saying that you should focus more on the goals and what you're trying to achieve in a particular block of code, and distill the abstraction of that task rather than focus on the mechanics on how to deal with, okay, what are my induction variables, what am I keeping track of, what are my variables, what should I mutate here. So instead of focusing on the mechanics of things, try to focus on the goal and see if there's a overreaching arch in what you're trying to achieve. See if there's an in-the-box utility that you can use. See if you can reach for an existing algorithm that achieves your goal or part of your problem, or if you can compose more functional elements to achieve what you want. And there might not be what you're looking for in the standard toolbox, whatever the language is. But for certain, you can create those primitives. So I'm not saying you should never create primitives. You should, but you should try to make up a sort of library of reusable components that you can easily plug together and achieve the task you set out to achieve there. So, yeah, okay, that was just to keep an eye on the chat window. It got covered up. So in general, we should prefer to use baked algorithms. In this case, as I'm talking C++ here, I'm talking about the STL algorithms, but in general, think about what it is in the box, what's offered by your programming language, by your standard library, by your third-party set of algorithms or packages that you're using. So think about correctness. There's fewer opportunities to write bugs if you don't roll your own. So there's so many things related to iterator validation when using STL data structures, or various silly mistakes like copy-paste bugs that you can do when dealing with iterators or for loops or sentinel values and conditions to stop or exit a loop or something like that. Range bugs like the I see somebody asking about the sound. I hope everyone is hearing me.
See, I hear you loud and clear, Victor. Can others confirm? Yeah.
Okay.
Okay.
So it wasn't me. Think about the famous off by one errors, like how far, when should you stop? Think about boundary conditions and early loop breaks and sentinels and guaranteeing loop invariance, for example. Think about what changes on each iterations, or what invariants need to be preserved so that the algorithm keeps working as it should. So and of course issues with the algorithmic logic itself that could be flawed, but in general a huge class of problems that are not specific to beginners, mind you. Very experienced programmers can make these silly mistakes. So it always helps when reusing well-tested components, and if they're standard components from a particular language or a framework, then they might be used by millions of programmers and hundreds of millions, hundreds of millions of programs in the wild. So I'm not saying they don't have bugs, but they're more thoroughly tested than our own code could be. So for sure that could help. And in general, code is a liability. The more code you have, the more bugs and more test units and more maintenance and documentation you have to do. So always try to have it as a goal to reduce code, to cut code. If you're working on an existing code base, try to eliminate code by replacing it with simpler constructs. So the ideal would be to have a negative line of code impact on your code base whenever you're going to be working in a team. So remove bloat to reduce maintenance and dependencies and sharing. So as little code as possible is better. Code is a liability, it's a contract. And clarity. Let's not forget that algorithm names, function names, say what they're trying to accomplish. So rather than having a block of code that you understand what's doing right now and hopefully might have a comment indicating so, or something that you might feel that's self-explanatory, might not be so for others or for yourself a few years down the road. So naming a function properly, having an algorithm with a standardized naming scheme, something that's recognizable, like a map algorithm, or like a find if algorithm, or like a sort. Those are keywords that raise certain expectations in all programmers regardless of the programming language or context. So it's always helpful when you're trying to build with a known set of idioms or known set of mnemonics that everyone understands what they mean. So algorithm names actually help. And even if you're building your own, try to use a consistent scheme and use words that have almost universal, unambiguous meaning. So if you're building something, an algorithm that finds something, try to have find in the name or something like that. Or don't try to be very creative with the names. Use something that meets the expectation of the reader of the code. So this is totally opposite of what a raw for loop can offer. So when you see a for loop or a block of code, you have to really read it, understand the stop conditions, what's happening inside, any kind of logic, any variables that escape that context to really understand what's going on. So try to construct blocks of code using well-known verbs. I have here find, sort, remove, count, transform, and so on. Things that are expected by fellow programmers. And mind you, a piece of code is read many more times than it's modified. So you should optimize for the code to be readable by humans, not by machines. So this will help build confidence for folks reading that piece of code, your colleagues or yourself a few years from now. So strive for clarity and unsurprising code. And simple code is more readable. Like I said, strive for being concise. I'm not talking code golf here, so don't name all your variables I, A, J, K, or N or something like that. So when I say simple code, I mean code that is composed of simple identifiable elements of vocabulary types that are universally agreed upon. So understandable code is expressive. Try to strive for fluent API, fluent interfaces that have meaning when composed together, functions that when juxtaposed have a meaning from a linguistical point of view. So they transfer meaning just by looking at the names. Be them verbs or nouns or something like that. So usually shorter means simpler, but not always. So when I say simplicity, I don't mean less characters. I mean unsurprising, things that are immediately recognized using established idioms in your programming language of choice or in your framework of choice. So unsurprising code is simple code. So, and of course, moving abstraction to and complexity to libraries has its advantages, like I mentioned earlier. So whenever possible, try to avoid reinventing the wheel. And if you have a component that you can reuse, try to reuse it. And whenever possible, extend what you have. So extend the standard library that you're using. Add new things to the toolbox. But try to add them in a manner that is generic. So don't try to have very specific implementations to your context. Try to generalize the problem you're solving and add to your set of useful functions, useful algorithms, add more to them so that you can leverage them in other places of your code base, in other projects that you move to. So building up libraries, it can be helpful, but your first choice should be to look up for something that's built in. Most probably you'll find something useful there. And we're gonna focus a lot today on optimizing code and strategies, more specifically optimizing for strategies for particular tasks. And in general, library writers and compiler writers think a lot about these things. So it's not guaranteed that reusing something from in the box, reusing some first class primitive in the standard library will give you the best performance, because sometimes they try to be fairly general. So a highly tuned, more specific algorithm might do a better job. But in general, they tend to be well thought out. And without properly optimizing and measuring, don't try to reinvent the wheel. So always go for what's in the box, measure, and if you can do better, then do better. But think about the sacrifices you're going to be making. about the choices in the context. So, and we're going to see today such examples. We're going to see how we can reason about standard idiomatic ways of doing some task using standard components, and see some disadvantages of those components in a specific context, and figure out together how to do a better job. So, and a main thing that I'm going to highlight today several times is the difference between performances and efficiency. And I would ask, if I could see a show of hands, I could ask who knows what's the difference between performance and efficiency. I don't know if folks can use the raise hand reaction or something. But in the interest of time, I'm gonna try to go on. So think about that vendor implementations tend to be highly tuned most of the time. I said that already, and in general, they avoid unnecessary temporary copies. They leverage move semantics for objects that can support such facilities. They tend to be highly tuned to be inlined away. So in general, there's no abstraction penalty for using STL algorithms and data structures, and in general, utilities from the standard library tend to be very friendly for the inliner. So you don't pay for those nice abstractions that you're using. And in general, optimizers do a great job about pointer aliasing and features like auto vectorization, auto parallelization, loop unrolling, and dependency checking all are highly tested on what's in the box. So by using standard constructs, standard library data structures, utilities, and algorithms, there's a higher probability that you can leverage these optimizations in the compiler better. You can do it on your own, but you have to be very carefully on how you lay out your data structures, how you're defining your operators and functions, so that you don't pay the abstraction penalties. Because you want to build some abstractions, you don't want to program in a very imperative, very low level. So I mentioned earlier about efficiency and performance. So usually when people learn computer science, especially from when coming from an academic background, they tend to learn about algorithms, and efficiency is what dominates in the back of their minds when they think about performing a particular task. And efficiency is about the amount of work that we need to do. It's stuff that is governed by the algorithm that we choose. Let's say we choose a quick sort versus a bubble sort. Yeah, so that's an obvious difference in efficiency, because the number of operations that we need to perform is drastically different in those two algorithms. So in general, folks tend to overly think in terms of efficiency. And the reality is that we don't program Turing machines. We program actual silicon. And this is where performance comes into play. And performance is governed by how fast you can do a particular work item, a particular step of the algorithm. And this is very much governed by your data structures. So the way you lay out the data structures, the characteristics of the data structure you choose for a particular algorithm, for a particular task, dictates the performance of that implementation. So these are not disjoint; they work together. But so they're not necessarily dependent, but they usually work together. There might be situations where a particular algorithm that we can choose for a task might be very efficient, in the number of steps, like it does a minimum number of steps to achieve that goal. But the performance might be horrendous in practice because of a poor choice of a data structure required by that algorithm, let's say, or a poor choice by the programmer to implement that particular algorithm. And then the performance completely tanks. So you might have a very efficient algorithm, but you might have horrible overall performance and overall timing for your task. So we always have to think about both and how they work together. And I cannot talk about this without referencing this classic book by Nicholas Wirth. I would ask if folks heard about Nicholas Wirth. If you heard about Pascal or Oberon or other programming languages, he did a bunch of experiments. So he was a great CS professor and language inventor. And this book, I don't know if it's in print anymore, but you can certainly find some copies somewhere for sale. It's an old book, but it's very much in the now. So thinking in terms of algorithms plus data structures is essential to constructing efficient software. So I would recommend, if you have a few hours to spare, to browse this book. Maybe you can even find some electronic versions online if you cannot get your hands on one. So highly recommend it. Very much a contemporary book, although it was written, I think, 30 years ago, if not more. Whenever we learn about algorithms, especially in school, we learn about complexity of algorithms, of operations, various operations, big O notation, amortized complexity, and so on. So let's say we have a cheat sheet like this one here. So we tend to focus on complexity analysis and the efficiency aspect of algorithms. And let's say who recognizes by this animation? Can somebody recognize this algorithm just by watching the animation? It's obviously some sort of sorting, because we're going to end up with a sorted sequence there. Paste it in the chat if you recognize it. It's a classic algorithm. Yes, we're partitioning work. So this is the classic quicksort algorithm. And it has an average case performance of n log n. Yeah, just as an animation. And this is where, yeah, I went too quickly, so people in chat didn't have time to react. People tend to focus a lot on complexity analysis and be blinded completely by the steps in processing a particular task, a particular algorithm, and completely forget about the data structures and the operations they offer us and the characteristics of those operations in terms of memory access patterns and memory layout. And I want to focus a lot on memory layout today. And so data structures, along with the operations they provide, they have complexity guarantees themselves, like a lookup structure. Yeah, I'm keeping an eye on chat. So if we think about data structures now, we can build a similar cheat sheet for various operations on built-in data structures from the standard library. Let's say for some of the operations on vector or on dec or list or stack or set map. So complexity analysis and complexity characteristics are not specific to some general algorithms. We have to think about various operations on the data structures that we're using, and how we're using a particular data structure in some task that we're implementing will severely affect the performance of our implementation. So we have to always keep in mind the operations that we're using on those data structures. And coming back to silicon, I said that we're programming silicon, not Turing machines. And even when we're talking about something like random access data structures or random access operation, there's no such thing as random access in real silicon. Everything has a particular cost, and we have to always keep in mind what kind of memory access patterns we're exhibiting for a particular operation, and how our data structures are laid out in memory with regards to the CPU architecture that we're targeting. So performance is about how fast the CPU can execute each step of our algorithm, and it's determined by the data types we use and our choice of data structures, about padding, about alignment vis-a-vis different CPU operations, and the memory access patterns through memory. So how well we're utilizing cache and so on. So we're gonna spend some time on that. And as a general strategy when thinking about optimization, because today we're gonna think about optimizing a piece of functionality, is you have to identify a problem. So you have to profile the application, identify worst performing parts, figure out bottlenecks in application, use a profile. Always benchmark, don't trust your instinct. You might think a particular piece of code might be unoptimal, not optimal, but in the grand scheme of things, that particular block of code that you worry about might be completely dwarfed by some other thing that dominates the overall operation. So intuition, I would say, most of the time fails. So don't trust your intuition with regards to optimizing. Always benchmark. From macro benchmarking to micro benchmarking, both matter, because things that might matter at a granular level when doing micro benchmarking might not be relevant in a grand thing in context. So they might change in profile in what dominates a particular grand operation of chaining multiple functions or microservices. So identify by performing tests and benchmarks, and learn how to do that properly so that you don't fool yourself, because you can easily fool yourself even when benchmarking. So comprehension would be the other part of the strategy, is to really understand what the code is trying to achieve and why it is slow. So don't, as soon as you spot something on the map, whatever software you're using to benchmark, as soon as you spot like something is hot, you complete your first thing would be to just go and quickly mess with it, try to fix it, try to find another way of doing it to improve it, and just rinse and repeat. So yes, that's gonna work sometimes, but you really have to understand the changes you're making and really try to internalize, why is it slow? Why is it, or even worse, you might be improving it, but you have to ask yourselves, why did this improve? I changed something and it improved, and I don't understand why. You really have to strive to understand why it improved, not just move on because, okay, hooray, it got better. And of course, iteration is key to just keep at it. So I'm going to skip this one because we're going to see it in practice. So we're going to narrow down this discussion, and I'm going to start to narrow it down from graphs and trees. I see a tendency of folks to reach out to node-based data structures because they tend to be very powerful in modeling various kinds of real-world situations. So graph data structures or trees in general, or in general connecting nodes in some sort of network of dependencies is a very easy way of modeling something that we need to solve. And sometimes we even identify very powerful algorithms that can help with these operations. So graph algorithms that can solve different things, or tree algorithms that can really help out. So I'm really going to try to focus the attention today on how we can go from trees and graphs and thinking about modeling our problem, our real world problem in terms of nodes. That's why the presentation is called Chasing Nodes, because I find that most folks are very comfortable with laying out problems in such a way in terms of dealing with trees or graphs or node-based data structures, and thinking about transformations on those operations rather than thinking more closely to the goal that they're trying to achieve, and more closely to the method, to the hardware. So we're gonna try to go from examining some algorithms and some solutions using node-based data structures and see some of their properties and how they can be good or not in practice. So I'm sure you're very familiar with graphs and trees. You've probably seen these a lot in courses and assignments and in books. So I'm sure you all know that trees have roots up, and they look like that. And I'm gonna give you just one example because we're gonna see today, and that is a red-black tree. And we're gonna see today because this has some nice properties with regards to space complexity and lookup operations and insert operations. So it's a rebalancing tree, but it's not a perfectly balanced tree, and it guarantees searching in logarithmic time, and it's used in the STL in standard map and standard set. And the reason I picked this one is because it's in the box. I talked about in the box elements. So I think more people should be familiar with the characteristics of this data structure and how it can be used, good or improperly. And it's a complicated data structure. So to this day, I think one of the best implementations of red-black tree is the one that was done by Dave Musser for Alexander Stepanov for what's in the STL. And although it's a very good implementation by many experts, this is agreed that this is a great implementation of a red-black tree. It has its particular niche of application and a particular niche where it really works well. So we need to understand this data structure because it's so easy to use, so convenient, but it's not always the best choice. And we're going to see why. By the way, if you want to drill down more about red-black trees and other similar data structures, I recommend this classic book. I'm sure some of you might be familiar with it already. So the reason it's so appealing and so many people go for it is because it's right there and it has such an easy to use API. If all of us should be required to implement some kind of balancing tree or a red-black tree, I think we all would stick to just using arrays. because it's a very difficult structure to implement properly and provide a good API for it. And the reason that it's so appealing is because it has a very easy to use API, and because it's projected as a regular type in the standard library, so it's easily composable. So you can easily end up building something that is a map, which is a red-black tree, that has might have a vector as a key, or you can have a vector of maps, or a map of map, or a map of sets. You can compose them because they're all regular types and project a uniform API that was very beautifully designed by Alexander Stepanov. We were so tempted to combine these in such an aggressive way to model something very close to what we're seeing in real world. So we are able to almost literally translate our requirements in composing such node-based data structures because their API is so appealing and so regular in usage that we may easily end up building a monstrosity that can solve the job, but can for sure tank performance. So it's this is one of the things that I'm trying to demystify here. Is I'm trying to raise awareness on how these data structures work, and when they're good and when they're not a great choice for our tasks, but for sure they're appealing. So let's explore together the properties of these structures by building a sort of a search engine index in C++. So don't think about something very fancy, but it is a database that acts like a search engine index with autocomplete and everything. So we're trying to build such a thing, a toy variant anyway. So, and this is going to work like we have a database with a lot of keywords in there, and we want to be able to load this database and rank it based on some frequency. We have some frequency for given expressions, given search phrases, and we want to load this database and rank it based on search frequencies, and be able to offer a sort of a autocomplete functionality. So as you type a particular keyword, you might see the topmost suggested searches that match that keyword. For example, if I were to type cruise, I would get the output you see here on the right: cruise line, cruise ship, carnival cruise, based on the most frequently seen search phrases that we have in this database. And it's not something fancy. It doesn't understand semantics or everything. So if you're searching for Tom Cruise, it's gonna match cruise lines and cruise ships. So it for sure it doesn't have any fancy semantic analysis or language skills. So it's just a plain keyword match. And let's see. So yeah, popularity. Okay, I think this is, I just put this in the slide for future reference. So it's the explanation. So I have this database that I composed. It's a text file and has all these search phrases with their search frequencies that I've done by just scraping some internet databases. And we're just gonna parse this database file, which is a text file, and build up all these search phrases and see the frequencies, rank it, and then be able to do queries for a particular keyword. And I'm going to demo it, so it's not necessary. So yeah, this is a small fragment. This is how the database looks, the keywords DB there. So it's just, it's a stream of search phrases, and we are going to have to measure the frequency of each search phrase. So the frequencies are not stored in the database. So you might imagine this as a continuous stream of searches that go into the database. We might consider that this database is ever growing. But we have like a snapshot that we're working with. Nothing fancy here. So we're going to have just a file on disk. So we have to load everything, measure the frequency of all the expressions there, and then be able to do some queries and show most popular suggestions based on frequency. So we're going to make some assumptions. And this is an important part of doing modeling. Doing modeling means understanding real-world workloads, understanding the requirements and the shortcuts that we can take when doing implementations, because all models are approximations of, of what happens. But we have to be in particular a good contract with what we need to offer. So we need to understand the choices that we're making. So this text file contains only ASCII characters, English words, in this case for simplicity. Keywords are separated by space or new lines. Database is considered a snapshot, so it's read-only. And each line represents a search phrase used in the past. And we shall consider the whole database file as a continuous chain of keywords separated by white space and new lines. So it might be like a stream, but we can consider it like a mutable snapshot for simplicity. And the keyword is a sequence of non-white space characters, so real words. I think it will make more sense when we see it in practice. So for simplicity, we shall define a search phrase as a pair of just two consecutive keywords in the query database. So the database might have may have tuples of words, of keywords based on things that have been searched in the past. But we are going to consider that a search phrase is just any combination of two consecutive keywords, like cruise line, cruise ship, Norwegian cruise, LCD, Sony, whatever, chip monitor, and so on. So this would be our meaning of search phrase would be a pair of two keywords, just so we have something that's easily doable in an hour. So our first task is to load and rank the keywords database. And that means ordering all search phrases according to frequency. And we should be able to print top 1000 search phrases with the respective ranks. So that's just so we can validate that we ranked it. And this is what a top 10 might look like. So real estate, for sale, New York, this would be the hottest things in the database. And our second task would be to implement the auto suggestion engine. And this operation should be super fast, like in real time, almost. So given a keyword like cruise, when we're in interactive mode, we should be able to see the actual result, like matches for cruise. And we're going to see two completely different implementations. So let's dive into the first one. I'm going to put code on screen now. Okay. Let me know how's the font. Let me go to the main. Just a second. Okay. How's the font? Is the font okay? Should I increase the font a bit? Looks good. Maybe increase it a bit. Just in case people have problems. I increased it a bit. So go through the boilerplate. So we have our first data structure, a keyword set. So this stores a unique keywords from the input sequence. So right off the bat, our first strategy is we have this database might be huge, and there might be a lot of duplicated keywords there, a lot. So our first attempt here is to eliminate any such duplication. So we're using a keyword set to store each keyword from the database just once, so that we avoid any duplication. And the keyword set is just an unordered set of strings, so nothing fancy here, right? Okay, and these are our keywords. And as we read through the file, we insert each word in the keyword set and get an iterator from this set. So we get the iterator in our keywords data structure. So this would be a current word iterator. And then we have a new data structure here, which says keyword tuple counts. So this stores a unique keyword, each unique keyword tuples and their frequency. And if we look at this data structure, again, nothing fancy here. It's a keyword tuple and a frequency, which is stored as a size t. And the keyword tuple, if we're ignoring the operations for now, and the keyword tuple is just 2 iterators. So again, we're trying to avoid any duplication here. Our strategy is to have 2 iterators from the set of unique keywords, again, avoiding duplication. And we have in our tuple is not 2 keywords, it's 2 iterators in that existing keyword set. So these would be iterators into this set. Yes. So, and going back to the population code, so at each run through, we insert this tuple. So we have the previous iterator. This is a classic while loop where we track the previous iteration and the current iteration. So we always have two such iterators that we're dealing with. So we store this tuple, you see here between braces, previous and current. So this would be the tuple we've seen earlier. So this is this keyword tuple, first word and second word. Yes. So we're storing this tuple and we're increasing the frequency whenever we discover this combination. So at each step, if we discover an existing combination, we increase its frequency. So it starts up at 0. And this map is between keyword tuple and its frequency. Again, I remind you, this is the map between a keyword tuple and its frequency, and it starts up at 0. And each time we encounter a tuple, we increase its frequency. If we see it the first time, its frequency would be 1. The first time we see it. So this is the code that populates this combination. And if a particular keyword has already been seen, then this iterator would return the position inside the iterator inside our set of unique words. So if a word has been seen before, we get an iterator to that word. So basically, we have a guarantee that an iterator into this set that is ever growing, never shrinking. So this set of ever growing unique keywords, we have an iterator to each unique word, and we keep track of these tuples of combinations of such words that we encounter in the database. Any questions so far on loading the the file from disk into our data structure. And then we print out keyword database was successfully loaded, unique keywords. We print out how many unique keywords we have, how many tuples we have, and so on. And then we have to rank it, because so far we didn't. So now we use another set of an iterator, so a set of iterators into our data structure that we populated, the data structure tuple counts. And we have a custom comparator that we use. And whenever we insert, this is a self-balancing structure. I remind you that the standard set is a red-black tree. So whenever we insert here in this line, whenever we insert, this comparator rebalances this tree and it preserves its invariant of being sorted. So standard set is a sorted container. And this comparator is, again, very simple. Whenever we have two iterators, so a comparator always gets two iterators to the value type of the data structure that we're attaching it to. So here it's applied on keyword tuple counts. So this is a comparator for this kind of elements. So iter I and iter j are iterators to this kind of structure, right? So we compare them by frequency. We see that the frequency is the second position in the map. That's why we're using second here. So we're comparing the frequency, and in case of equal frequency, when the count is equal, we compare by keyword tuple. This would be a classic comparison by parts. So we have a structure that has two parts. First, this is first keyword tuple. Size t is second from here, from this algorithm. So whenever we compare a structure by parts, this is called a lexicographic compare. In general, like a generalized lexicographic compare. Don't think about necessarily a dictionary, but it's something like that works like dictionary order. So whenever we have a pair or a tuple and we compare it by parts, it's called a generalized lexicographic compare. So we try to compare by frequency, so just by second here. And if we fall through through both these if conditions, that means that the frequency was equal. So then we compare by the first part. So this is how lexicographic compare works. So we have to compare by one part, and when we have equivalence by one of the parts, then we compare by the other part. So this would be the second part of the object, which is the tuple itself. And the tuple itself has an operator provided. This is the one we're calling here, and it's the one I hid below. And the keyword tuple again implements a lexicographic compare. So we compare by the first word because it has two parts, first word and second word, and we have them here, the two words, which are iterators. And again, we compare by the first keyword, and in case of equivalence by the first keyword, we compare by the second keyword. Again, this is just mostly boilerplate, but this would be generalized lexicographic compare. And in this case, because when we're dereferencing these iterators, we're actually dealing with strings there. It's actually lexicographic compare. So it's nothing fancy. It might look convoluted, that just because C++ is not the most concise language in terms of how it looks and verbosity, but it's just boilerplate. And if I would have chosen a generalized, like a standard pair, for example, instead of using this tuple, I would have used a standard pair, then I would have gotten this operator for free. But I want it to be very explicit and using my own data structure here so that I can show what happens. But if you're using a standard pair or a standard tuple, to do something like this, you get these operations, this lexicographic compare, you get it for free. So you can do standard lexicographic compare using standard pair and standard tuple. Remember that. But I just wanted to show how it works. That's why I chose to be very explicit about this structure. This could have been a pair with these two iterators. Okay, coming back to our implementation. So we're inserting into this red-black tree, and we're using this custom comparator to keep it balanced and sorted the way we want it, based on the frequency. That's what we want. So our comparator sorts by frequency, and in case of equivalence, sorts by keywords lexicographically. So this is how we ranked the database, and then we just output it. This is just boilerplate for outputting the database. And the second part, where we want to search a particular keyword and find most frequent searches related to that keyword, because our structure is already sorted by frequency, then we just need to traverse, and we have like a top 10. We requested the task request to print the top 10 search phrases for that keyword. Then we just have to take the first n, the first 10 elements of this sorted thing. So we're just gonna traverse this sorted structure. So now top keyword tuples. See that I gave it an intuitive name. So because this structure is ranked, I named it top keyword tuples. And now we're just iterating this top keyword tuple structure and stopping after and stop after match count elements. So after 10 elements, we stop this loop, right? So we're at each step, we're checking if the search thing matches the keyword that we want to pull out. So we consider this a match if it matched the input keyword. So again, this is just boilerplate for retrieving those matching tuples. The key here is that our database is already sorted. It's already, that's why we call it, it's ranked. And this is achieved by this complex data structure that we have chosen, our standard set, our red-black tree. So this is what we chose to do it. So, and I have a different implementation. Questions so far on this implementation? I see perfect here then in chat. I think it's related to the font size, not necessarily to the quality of implementation, right? Question, why do comparators need to be friend functions? They're referring to what I have here. So the reason is symmetry. This could have been implemented as a member function, so bool operator less than const keyword tuple ampersand other. So, and the implicit first argument would be this, because it would be a member function. You could implement the operator like that, and until C++20. That's a side story. If you want to explore, we can chat about C++20 and spaceship operator. But you could have chosen to implement it as a member function. But then you have an asymmetry in terms of when you can use it on the left side or on the right side of a particular expression, because it's implicitly bound on the left by this this reference, this pointer of the data structure, because it's a member function. It's not a generalized function. And another approach would be to have it generalized, would be to take it out, like have this function, instead of being friend here, have it outside the scope like this. And let's assume it's the same implementation. So it would be like this. So the operator is on the outer scope of the data structure now. And again, it has left and right because we want this symmetry. So be able to have it on each side of the expression and on all types of value categories associated with that kind of expression, what's on the left, what's on the side, and all the combinations there. And we can take it out. If we take it out and have it like this, it would be found by a mechanism that it's called argument-dependent lookup, and it would be found in the proper namespace of the where it would be looked out. The disadvantage of having it outside is that from more like a code organization point of view, you would have to mentally know that, okay, these operations that we might have here, for example, we might have a bunch of operators and operations here for this particular structure. They would have to somehow mentally be grouped with this structure because they belong to these structures. They're companion operations for this data structure. And we don't want them inside because we don't want this parameter to be left bound. So we want to have two arguments to these functions, but we want them logically to be grouped with this data structure. So we might be forced maybe to put them in some namespace or not. That might complicate things or not, but they would be logically associated with this data structure. And another reason why we prefer them to use this trick to have them friend inside the structure is that by having them inside the structure, we have them automatically in the lexical scope of the structure they belong to. So they would be, we would be leveraging the namespace utility of grouping them in that structure, although they are not member functions. So mind you that having them friend inside the structure does not make them members, but it has the advantage that we can access private things. For example, if in our implementation we would have needed to access some private, this structure doesn't have any private members, but if we would have the need to do something here in the body of the implementation with something private to this data structure, we could have done that in this approach of having them friend in the structure. So this is a way of accessing private state. For example, think about implementing an equality for this structure. We might want to compare something that is private in nature. And if we were to put this outside the structure, then we couldn't reference that private part in our equality comparator, let's say. Might make sense or might not make sense for what you're choosing. So equivalence and how we define equivalence relations for types is a whole other discussion. I have a different presentation about that. You can just Google my name, and it's called regular types and why do I care? Regular types. I have a whole 1-hour presentation about regular types where I go into details about this. All right. All right. No more questions regarding this. Okay, let's move on to another strategy. So what we've seen so far is loading the keyword database in our data structure, counting search phrase currencies. We fill the standard map from each search phrase combination to its frequency. We used red-black trees in using standard set and standard map, and we used iterators everywhere to avoid copying strings. So we never copied any string from the database. So once we load it, we stored every keyword unique from a single location. So we're always using iterators from that standard set. And ranking is done automatically by the means of the custom comparator predicate that we have seen that is attached to that standard set. So each time we insert in the set, it's automatically rebalanced. Advantages. It's a very good showcase of STL usage. It's textbook, I would say. And that's not a good thing, by the way, when I say textbook. And it is succinct. I think the implementation is compact, ignoring the boilerplate of loading the file and the boilerplate regarding the comparators that we need to provide, and everything that's sort of mechanical in nature. It's not algorithmic in nature. It's succinct in implementation, and it's relatively easy to explain and understand. So as you read this code, you see idiomatic usage of standard set, standard map, and iterators, and plain data structures that just have two iterators inside. And so it's not complicated in nature. The algorithm is hidden inside that complicated data structure. So it uses simple ordered STL tree data structures like standard set and standard map, idiomatic STL usage, like I said, textbook. It is type safe and memory safe, offers good performance characteristics for fairly large data sets, so it's not that bad. It stores unique keywords, so there's no duplication, so it's very it's very compact, so it's very space efficient. But it has a good working set, yeah. It has some disadvantages, so we're gonna focus on that. It's not cache friendly. It uses node-based data structures that are spread all over memory. So all those nodes in that tree, in that red-black tree that we saw in the diagram, all those nodes that we're inserting, all those tuples of iterators are spread out through RAM all over the place. So, and when we reach out during the algorithm, we reach out for various nodes, and we have to jump around in memory, and we're thrashing the cache. So the CPUs don't like that at all. So in terms of idealized Turing machine, that's perfectly all right. When dealing with actual contemporary CPUs, they hate that. So actual contemporary CPUs want data locality. They want stuff in memory that's contiguous, and they want to access elements in memory in a predictable pattern, not jumping through all sorts of indirections. Remember, we kept using all sorts of iterators because we had a central location where we stored all the keywords in that set of unique keywords, and everywhere we were using iterators and indirections. So one more level of indirection, iterator to that structure, iterator to that tuple, and so on. So all sorts of indirections to address stuff. So that might build a very intuitive model. Like I said, it's very easy to understand and model the reality, model the task into our program, but it's not friendly at all for the computer. So tree data structures are very memory inefficient in terms, they even waste a lot of memory because all those iterators behind the scenes, they're pointers, and they end up to be 64-bit pointers, so might be a lot of waste. And you might say, oh, compared to the keywords, it might be very efficient. Let's see about that. And of course, it uses notorious slow IO streams, but that was just for program brevity. In real world, please never use IO streams. Always go for standard print or standard format in modern C++. And if you cannot use C++ 20 or 23, at least use the FMT library to have way better performance than IO streams. But that's just for brevity and slideware. Okay, and we're doing case-sensitive compare just for simplicity. And now, moving to another approach, and the second approach would be quite different. And the second approach is a bit more convoluted, just ignoring a bit of boilerplate, reading the file. And again, we have keyword tuple counts, the first structure we're seeing. And keyword tuple counts, now it's a different structure. Now it's an unordered map. Now, the name might be weird, but it tries to deliver the semantics. So as the name says, it's no longer a sorted structure. It's an unordered structure, and it's no longer a tree. So we're no longer dealing with a tree structure there. This is not a red-black tree. This is a hash map. So I'm assuming a bit of familiarity with hash maps. If someone has questions about hash maps, I cannot go into details because we don't have time, but I can give some clues. Basically, it's a means of creating an associative data structure that guarantees very fast lookup based on the key. So it's a key, here string is the type for the key, and the value, a payload, whatever type that might be. So it's a key value pair associative data structure that ensures very fast lookup operations. So finding something by key, not by the payload, but by the key. Okay. And again, it's not a tree. This is not a tree data structure. It's not a balanced structure in any way. It's a hash map. It's not the best hash map. The standard one in STL. It's a good-ish hash map. So for better workloads, better performance, there are multiple alternatives out there, like flat maps and various other alternatives. But it's a good enough hash map for general use. So if you want to go that rabbit hole, I have another presentation. I think it's called So You Think You Can Hash, where I show more details about hashing algorithms and using hash data structures and composing hashing on aggregate data structures. All right. If you have questions about hashes, paste them in chat and I'll address them later. All right. So we have our first data structure. So it's a hash map from a string, which implies it's a keyword because we don't have any other strings in the program, and a size t, which probably is the frequency. But it's not a plain string. We use a trick already. So we have our first trick that we use here. And if we look at the way we read the file, we see that we have this is the hash map. So we have, again, the dance of the iteration with the previous word and the current word. So nothing special here. The difference here is that we're no longer using a set of unique words. So right off the bat, we're going into uncharted territory. So we full on decided we are okay with storing duplicates. So it's a totally different way of thinking about this. So we are okay with storing duplicates. And the way we store these keywords in our hash map is by concatenating the previous and the next word. So we're reading a word stream. Yeah, word, keyword. Yeah, and we're just concatenating 2 by 2 keywords. So immediately we have a lot of waste. So a lot of wasted memory. We're storing a lot of duplicated keywords here. So I said it's a totally different approach here. And we're just incrementing the frequency. So this is a simple associative data structure. So this is the concatenated. So they're stored just like this. You see this example, keyword 1 space keyword 2. Just like that, we're storing them. And we record their frequency, because this is what we need to track. So just like before. But this time, no fancy iterators, no pointers, no indirections, no unique storage of keywords or nothing. We store them with lots of duplication. All right. And then we have a vector of these keyword tuples. So this would be a vector of iterators into this data structure here. And we're just inserting them in a vector. So far, nothing fancy. The reason we're inserting them in a vectors is that so we can sort them, because we want to sort them, and you cannot sort something in a hash map. So we need them in a hash map to keep track of this frequency, because we need fast access to this frequency element of the tuple. But we need to sort them, and the hash map doesn't support sorting. And we do another step where we trade space for speed. So again, we take on a new data structure here, a vector, but we're not copying anything. We're just storing iterators into this hash map. which is stable at this point. We're no longer populating. So at this point, we're done populating it. So these iterators are stable. And we just construct a vector, but I'm careful to reserve capacity for this vector because I know upfront how big it's going to be, and I don't want to surprise reallocations. And then I sort this vector by what? By the frequency. I don't need to use any custom predicate here because I just need them to sort by frequency. Here, iterator second would be the second in this data structure, which is the frequency. So iterator is inside this data structure, it's iterator to a map, an unordered map, and we're using the frequency. So the comparator is, it can be already in line in this lambda function. So I don't need to build a separate comparator. I could, but I don't need to. It's too trivial. It's just a comparator by two integers here, which is the frequency. And that's it. I ranked the vector. And what I do now is this is what prints them to file. Nothing fancy here, just mechanics. And now I need to find suggestions for the input keyword, like before. So the same functionality. And now I have to do a bit more convoluted work because I took a shortcut earlier. I took the shortcut of concatenating two words, smash them together in a single string. So I took that shortcut to gain speed when ranking the database, but I'm gonna pay the cost for that shortcut I took. But I'm gonna pay that cost when doing the lookup and only when analyzing particular matches. So when I'm trying to find the matches for that input keyword. So I'm searching to find to find the separator. In my case, the separator is just a blank space there. So I'm doing a compare, a case sensitive compare in this case, and I'm trying to identify in my smashed tuple, I'm trying to identify the input keyword, which might be on the left side or on the right side of the separator. And I consider that a match. So I'm paying that cost, but it was a deliberate design decision to organize the data structure in a different way and moving this cost to the lookup phase. And let's see. So it was a totally different approach. And to sum it up, so we chose a hash map, and we leverage the fact that it's very speedy in storing the new search phrase and finding existing tuple. So it's constant time in lookup. The usage of the custom predicate is optional. So it's not mandatory to perform a stable sort with regards to the search phrase. And the loading of the database, we're just filling the unordered map, the hash map, with this tuple and its frequency. And we're ranking it using an auxiliary data structure, which is the vector, and applying a standard sort algorithm with that custom predicate, which does lexicographic stable sort or not, or we can just compare by frequency. We don't care about the detail. And it is succinct in implementation, like before, relatively easy to explain, assuming someone is familiar with hashed containers. So it does assume familiarity with a different data structure. It is idiomatic STL usage. It is type safe and memory safe like before. Good performance for large data sets. It's very fast due to the hash-based lookup. And what is important here is that although it duplicates a lot of data, its memory usage is lower than solution one. It's not intuitive, but in our particular data set, because we have relatively short keywords in our database, and solution one has a lot of memory waste due to a lot of tree nodes, and 64-bit pointers. So each time we used an indirection, we used a lot of iterators. Those behind the scenes have pointers, which are 64-bit in length. And the tree nodes themselves, the tree nodes have pointers to parent and left and right children and stuff like that. So the tree node itself is a wasteful data structure because it's an intrusive data structure. It has pointers to connect to adjacent nodes. So this is an important distinction. A tree-like data structure has a lot of intrusive information to connect it to its network of other nodes, whereas a continuous data structure, like a vector, for example, it has an implicit connection to its neighboring nodes, so to speak, and the implicit connection is the next one. So the next size of T in memory. So the implicit connection is by adjacency in memory address. So having a contiguous data structure eliminates a lot of these extra pointers that can generate a lot of waste when dealing with very large networks. So in general, people don't tend to think about pointers as being wasteful. They think, it's just a pointer. It's like an integer. It's not something big. But when you add up for each node, you add up 2, 3 pointers, and you have millions of nodes. You get a lot of waste, especially on 64-bit systems. You get a lot of waste. If you put these nodes or iterators in other data structures, there are padding concerns. So if you don't align data members properly, you could end up having even more bloat for your nodes or for your structures, because the compiler needs to do some alignment if you have like different kinds of types of data members in there and they're not properly aligned. So you can generate, it's not intuitive, but by duplicating aggressively the keywords in our database, we actually have a lower working set than the node-based solution we had in solution number 1, where we were very conservative and wanted to have to store each keyword just once, but we were using a lot of indirection. So yes, it stores duplicated keywords. So we might be uncomfortable with this. And it offers poor memory working set scaling for long search phrases, so due to duplication. So if our workload would involve very long search phrases, then concatenating those as we did, so our approach could end up being tipping the trade-off on the other side. So that's why I said we always have to measure the working set and how we're doing based on real workloads. And again, some of the other cons that we had in solution 1 as well. So questions so far. I have a few generalized advice here, and I have hints for you to get this even further, to think about a third possible solution or a fourth possible solution. So of course, with regards to I/O, great simplification would be to use something like a memory mapped file, so that we map this into memory, the existing file on disk, and have those keywords mapped into process memory without the need to actually read them from disk into RAM. So that would be a classic technique of avoiding unnecessary I/O and having a window to stream through that memory mapped file at ease from disk. That would be one technique. That's an obvious candidate for improvement. Of course, we can perform a partial sort on the keyword tuples because we know we just want the top n. So that would be helpful because we had in the second solution, we had a standard sort there in code, and we sorted the whole database, but we only cared about the top n search phrases. So again, might be a trade-off that we might be inclined to take, depending on the workload. And again, I reiterate, using a cache-friendly data structure like a standard vector to store the tuple counts in an even more compact way. So avoiding even the hash map. So even the hash map is that we used in solution 2 is not a cache-friendly data structure. The solution is better than the node-based one that we used the first time around with the red-black tree. But even the hash map is not a cache-friendly data structure. It's not a contiguous data structure. So rethinking in terms of arrays and how we can use contiguous data structures like arrays and vectors and sort them and count adjacent equal pairs could guarantee an even a superior solution here. But it would get more complicated. So one of the cons on solution 3, let's say, would be that it could get a bit more complicated. So going for array data structures here would be the obvious optimization path to take, but the solution will no longer be necessarily trivial to explain or trivial to implement. We need to take some shortcuts, to do some clever things, to keep track of adjacent pairs and so on, and think about duplicates and so on. So, but again, it's a cost that might be worth paying to squeeze the maximum performance here. And there's so many tricks that we can leverage based on the real workload. For example, when dealing with English words in this thing that we have in database, we can truncate the words to 8 bytes each. Because if we do a survey of the database, we would see that over 90% of the words in the database are below the 8 bytes boundary there in length. So we can store them as 64-bit integers. So that would be even more efficient because now we're doing operations on integers, which is even faster than doing comparisons and hashing on strings. Because whenever we're doing hashing, before we were doing hashing on strings, and those could be expensive. But if we're doing hashing on 64-bit integers, those are way faster. So we can do all sorts of clever things that might be good enough approximations for the problems we're trying to achieve. And this is and I'm a bit over on time here, but this is a trend I'm trying to identify here. And in general, we have to understand the context, and we sometimes need to be very aggressive in pruning the input domain and restricting to realistic values in the natural workloads that we're dealing with. So over generalizing a solution might not be what we need in a particular workload. So grouping classes of values based on the frequency of occurrence in real world, or cutting out particular values or types of values from the possible input domain to simplify the task, the algorithm itself, can end up being a tremendous advantage. But we need to study and understand the restrictions and the invariants that we have for our problem, for our task. So, of course, there are opportunities to parallelize things and identify operations that can be split and executed in parallel and reduced then. I mentioned already arrays as a very fast path to performance there, and thinking of structures of arrays rather than arrays of structures. So distancing ourselves from the OOP style of programming and getting closer to data-oriented design. And I would recommend that you see presentations by Mike Acton on data-oriented design, or Andrew Kelly. So thinking about memory alignment, I mentioned earlier, padding and alignment for data structures, and be very careful how we lay out fields in our structures, and if we're designing them to be cache friendly or not, and if we're wasting cache lines when doing the memory access patterns for our structures. So all these things are general techniques that are language agnostics, and we need to keep in our heads when searching to find optimization opportunities in our algorithms, and think about ways to identify opportunities to change things, to simplify things, to reduce the problem to something that's equivalent but easier to process, map things to bits if possible, bit fields, and replace expensive logical operations with bit operations that might be very fast. So these are all such opportunities. And a very recent addition to this slide deck is a very interesting case study, I would say. It's a 20-so minute presentation. I don't know if you're familiar with Matt Parker from Stand Up Maths. If you're not, highly recommend it. It's a wonderful channel, very instructive. So he just published recently this video, and I thought it was a perfect match for what I was trying to convey in this presentation. And he did a small puzzle. It was something about generating all the possible 5-letter anagram combinations and that yield dictionary words or something like that. It's not important. The problem is not important itself. So he did an implementation in Python that took I think he said 30 days to run. It was one of those implementations where it's not a bash on Python itself. So it was one of those things where he translated the requirements of the problem directly in code, and without any concerns of optimizing and finding the perfect way of representing them. So modeling, as we did in solution 1, so the most intuitive, natural way of translating the requirements into code. And it was horrible for performance. And then a lot of folks on the internet just jumped in and offered alternative implementations that were way faster. And again, some of the stuff they did maps perfectly to the general techniques that I recommend here in this presentation. So they did, of course, they did it in a lot of programming languages, from C++, Rust, Java, Python, and so on. So they did it in a lot of programming languages, and it's not, the clear winner is not related to necessarily a particular programming language that they choose, but rather to techniques they use to simplify the problems and to map it to hardware as closely as possible. So as distant as possible from the natural modeling that Matt did at first. So it's a fantastic case study. So, and it's fun. He's a funny person. So highly recommend that you watch this presentation. So somebody improved the code tremendously. So now that generator for keywords works in under 1 millisecond or something like that. So think about that. From 30 days, which is kind of silly if you think about it, to 1 millisecond. So, so again, if you watch that video, you're gonna identify all these bullet points that I have here. So the same techniques and strategy. And by the way, I forgot to prove that it, yeah, I know I'm out of time, but if folks bear with me, I'm gonna just run the code sample. So have to compile this is the second one and the first one, just to make sure I don't cheat. And the first one, I'm gonna time the ranking on the first one. Counting.
And as this is running, if folks want to think of some questions that they want to ask Victor
Yep.
towards the end, please take that time.
And also paste questions and comments in chat, and I can address them offline as well. So we have about 21 seconds for the first implementation. And the second strategy that we've seen, so the first one was the one with standard set and red black trees and everything, and the second one is about 6 seconds. So I would say it's a noticeable difference in performance there. And just so you know how it works, if I'm searching for something, a cruise line, crypto, everyone wants crypto, but it's not the crypto you would think. Okay, that's about it with the with the demo. I forgot to show it that it's actually faster. And a quick shout out because it's December month. So I wanted to have a quick shout out to Advent of Code. So if you're not familiar with Advent of Code, highly recommend it. It's a good way to brush up on the techniques that I showed here. There's fun puzzles, one each day. We're on day 5 now, so each day a new interesting puzzle. They're funny. They have a backstory. They're algorithmic in nature. So some days you're gonna get away with a solution that is quick and dirty, but very inefficient. But there are gonna be days that are gonna be they're gonna punish you if you don't go for an optimal solution. So they're gonna force you to find a good algorithm, an efficient way of implementing it. But it's a good way of practicing these techniques and these optimization opportunities. So take advantage of this opportunity, folks. They're not restricted. So if you don't have time now, you can do it anytime. So you don't have to do them in sync. So you can do them at your own pace whenever you want and in any programming language that you desire. So shout out to Advent of Code, folks. So I'm done with what I had for today. If you have questions, I'll be around as long as you need me, or I'll be answering in chat if you want that way.
All right. Well, in the meantime, while folks are taking time to write in some questions, let's give a virtual round of applause, Victor. That was a wonderful talk. I think we all learned something here. And I think you've given students some homework for winter break here with Advent of Code,
Yeah,
which is wonderful.
That's fun for sure. You won't regret it. It's something that's gonna help you to build up your algorithmic skills and programming chops in general.
Yeah, wonderful. I wanted to start off with a question just as folks were thinking, because you had many things that I'd like to quote, but one that came in particular was, understanding why code is slow is important, but also why the code improved. I think that captured a lot of your talk. I was wondering if you could throw out, some example tools, profilers, things that students, even you showed at the end just the time tool, but any in particular tools you'd encourage students to check out?
I didn't want to do this, transform this in a presentation about benchmarking because that would be a whole other side adventure. But there are tons of tools out there. So depending on the platform you're using, they're going to be different. So if you're on Windows or Linux or Mac, there might be slightly different tools there. But there are profilers out there from free stuff to commercial profilers. For example, on Windows, I'm a big fan of Intel vTune, if you're familiar with that one. If you find it a bit too complicated to start with, it's a more advanced kind of tool. Maybe start with the profiler that's built into Visual Studio. I have to plug that in because I work on Visual Studio. So you could start with the profiler in Visual Studio, which is I would say is much friendlier in terms of UI and getting started and getting feel for using a profiler. I use a bunch of benchmarking frameworks like Google Bench, for example. So learn Google Bench. It's very easy to start up with. If you want the quickest way to the quickest gateway into, I would say, into, let me put up a browser window here. So let's say it was called QuickBench. QuickBench. So QuickBench is done. I had like a moment where, like a senior moment, and I couldn't remember the name. So it's done by my good friend friend Fred, Tingo, and it's a good way of getting started very quickly. So you don't need to learn how to set up Google Bench in your project or pull down the framework or installer profiler. If you wanted the quickest way to run a benchmark on a piece of code, you just this would be like a compiler explorer for quick benchmarks. And it's not a perfect tool, so it runs in the cloud. You might get noise. It's a multi-tenant kind of environment, but it's a it gives you a good gauge. So if you want a side-by-side comparison of two pieces of code, you have here like the blue and yellow one here, and it's a, I would say it's a very good proxy to get a feel for the thing that you're trying to improve, or get a feel compared to different approaches side by side. You might get different, more precise numbers if you run Google Benchmark on your PC, for sure. But I would say this is the gateway to benchmarking. So start with this one, folks, to get a feel for it, to build your muscle to compare pieces of code, or when you're iterating a solution, have your iterations here. You can have as many as you want, not just two. So you can have as many implementations as you want here. So to build an intuition for what you're doing. So start with this one. Then pull down Google Bench or any other benchmarking framework that you like. I prefer Google Bench. Pull down the package for your ID and whatever integration you want to set up there, and run it locally. And the next phase is figure out how to use a profiler like Visual Studio Profiler or Intel VTune or any other profiler that you feel comfortable with. On a Mac, there's fancy tools with UI on instruments and so on in Xcode, and those are again very friendly for beginners to get a feel for how it works. Some of the command line ones might be more unfriendly to start with, so it's a good way to start. So yeah, Quick Bench would be my #1 recommendation there as the gateway to learning how to benchmark.
Perfect. Thank you. Any other questions from students? I'm just looking at the chat here. I know some folks might have to go or start getting ready for the next round of classes here, but we'll just give a moment. We just have some comments. Yep. Keyword search appearing fast in Google. I'm sure they're using lots of these techniques that you've put together. I know from just, even looking at that last slide there and some of the resources you put, that's a good chunk of some of our performance course. So a lot of our students are going to spend some time learning about these things if they haven't already seen them in the next semester.
Super.
Right. Well, let's see. I think that's it for questions. So maybe we'll kind of wrap up since we're past time here. But again, let's give a virtual thumbs up and a round of applause. Victor, this was wonderful. And thank you so much for taking time out of your day to show us these tools, show us a great experiment. And, we all learned a lot from today's presentation. So this was fantastic.
It was a pleasure being here virtually.
Yep. So again, thank you again. And Victor, if you want to hang around for a few moments, we can chat. And yep, thank you to all of our students who came in today, and we'll rebroadcast this as well at a later date for students who weren't able to make it at this time.
Yep. See you, folks.